All right, guys. Hello again, and welcome to G Squared Academy, where excellence is epitomized. In today's video, what we're going to be looking at is the June 2022 paper. You can see me circling that right there, right? And this is paper 2, Csec chemistry. So let's get right to it because we have a lot to get through. All right. Let me just zoom this in so you guys can see what's happening here. So an experiment was carried out to determine the energy change for the reaction of magnesium metal and hydrochloric acid. The procedure is given below. 100 centimeters cube of zero point 0.5 molar hydrochloric acid was measured and placed in a calorimeter to make sure temperature is constant to some extent. Sandpaper was used as a to clean a strip of magnesium ribbon until shiny, and 0.48 grams of this was weighed using a balance. And then the temperature of the hydrochloric acid in the calorimeter was measured every minute for 5 minutes until a constant temperature was obtained. The magnesium strip was then added to the calorimeter with hydrochloric acid while stirring with a thermometer. The temperature was recorded every 15 seconds for 2 minutes. So that is what we have so far. That's the first bit of the thing. So let's see what now. So here you have our readings. And when they give you questions like this, guys, you have to maximize the marks. You have to make sure you get these marks. Okay. So you're supposed to read it. And so here you have now your table with all those readings, right? So make sure you read your readings correctly, because you don't want to waste these 5 marks just for reading a thermometer, right, to give you those readings. Then now they say in the questions, using the grid provided on page 7, plot a graph of temperature against time using the data in table 1. Draw the best fit curve through the points. Right, so again, these are like free marks, so don't lose them. Okay, so we're going to press on. Okay, and we're not at the graph as yet, but we'll see what's going on. Use the graph to determine the temperature range, the temperature change delta T for the reaction. So here's the graph, right? And I'm just zooming in a little bit over here now so you guys can see what's going on. So there's the graph. And of course, the temperature increases, right? And then it stabilizes a bit. Of course, you do this and make sure you circle your points, right? Because that's one of the things as well your examiner may look for, that you circle your points, or you use X to mark your points. You don't need to worry about scale necessarily, but they may ask you for the scale for this. But make sure your best fit line is nicely drawn. Okay, so we are asked now to determine the temperature change. So how do we do that? The initial temperature was down here, right? And then now when the graph plateaus, you draw a line across and you interpolate this temperature, which is something like about 45 degrees Celsius or something like that. Okay, so that's when it plateaus. Okay, when the graph plateaus, that's where you draw it, or your highest temperature really that you'd get. But you have to use the graph, and you have to show on the graph that you have gotten that information. Okay, so then now, once you've done that, let's go back to the question. So we're going to say that it's 45 degrees Celsius. Okay, so it is 25 minus that. So initial was 25. So 25 minus 45, what's that? 20 degrees Celsius, right? Something like that. Okay, so now it says state one difference between endothermic and exothermic reactions. There are so many things that we could say, but one of the main things is that an endothermic reaction releases heat into the surroundings so that there is an increase in temperature in the surroundings. Okay, that's one thing. While an exothermic reaction releases heat into the surroundings. An endothermic reaction removes heat from the surroundings so that there is a decrease in temperature of the surroundings. Another thing you could look at is from the energy profile diagram, which I have shown in previous videos, that the energy of the products in an endothermic reaction is greater than the energy of the reactants. Okay, and another thing is that for an exothermic reaction, the energy of the products is less than that of the reactants. One final thing just to say, endothermic reactions are less popular than exothermic because the activation energy for an endothermic reaction tends to be pretty high versus the exothermic reaction. Okay, so let us proceed. Okay, so that's one difference we could have stated between those things. Now, state whether the reaction between magnesium and hydrochloric acid is endothermic or exothermic. Let me zoom this in just in case you're not seeing it. So we want to state whether it's endothermic or exothermic. The easiest way to determine if something is endothermic or exothermic is to determine if, or if is to see if there was an increase in temperature with the thermometer or a decrease in temperature. We know for sure that the temperature increased from 25 degrees Celsius to 45 degrees Celsius. So this is an exothermic reaction. Okay. And so you write that down, exothermic. And so let us press on. All right. And of course, this was our graph that we went through before. Okay, so let's see now. It says now write a balanced chemical equation including state symbols. Some students seem to forget about that part for the reaction between magnesium and hydrochloric acid. So what we want now is magnesium is a solid, right? Plus hydrochloric acid, which is aqueous. All acids are aqueous, generally speaking. And that produces magnesium chloride, which we're going to call aqueous as well, plus hydrogen gas. Okay, and of course the equation must be balanced. So we're going to put a 2 right here. Let me change the color for that one. We're going to put a 2 right here. Okay, so not right here. We're going to put a 2 right here. So now we have 2 HCl, 2 chlorines, 2 hydrogens over there. And we're all good. 1 magnesium, 1 magnesium. So we're good to go. For things like these, guys, you must make sure you accumulate the marks. Okay, so let's look at the next bit of question now. It says calculate the number of moles of magnesium used. So there's a little space right here, so I'm going to do moles is actually equal to mass divided by molar mass. So they're not, you probably would be given a periodic table, or you may need to remember the molar mass of magnesium, which you, well, actually you don't, it's right there. So this is great news. The mass that they used was 0.48, if I remember correctly, and I'm just going to double check that. All right, so make sure that it was 0.48 and go all the way back. This is so far back. Right, there it is. So 0.48 grams. Okay, and so now we can calculate the number of moles. So the number of moles right here, 0.48 grams divided by 24 grams per mole. Okay, and so when we do that, our calculation yields 0.02. So 0.02 moles. And please show your working. That is very important. Okay, so we press on. Now it says determine the volume of gas that would be collected if the reaction took place at STP. And notice they have given us what STP is right over here. That would be collected if they. So what we're going to do here is we're going to make an assumption, even though we don't. This is 3 marks. We shouldn't really make an assumption, but we're going to make an assumption. Okay, I said we're going to make an assumption, but we're not going to bother to make the assumption, having checked the information that he gave us. Now, this question really is asking us to look at limiting reagents. That's really what it's asking us to look at. Now, we have the moles of magnesium, which is 0.02. We just calculated that. What we need to do now is calculate the moles of HCl. In the question, they actually gave us how much HCl we are working with. See it right here, 100 centimeters cube of 0.5 molar HCl. So we can actually calculate the exact amount of HCl which is in this reaction flask. And that works out to be, this is what I've done over here. So 0.5 moles is in 1,000, because that's what molarity means, the number of moles in 1,000 centimeters cube, or 1 dm cube. So how much is in 100? And then you cross multiply, and I got 0.05 moles over here. So I'm working with 0.05 moles of HCl. Now, the ratio of magnesium to HCl is 1 to 2, which means that for every 1 mole of magnesium I have, I need 2 moles of hydrochloric acid. I have 0.02 moles of magnesium here, which means I need 0.04 moles of hydrochloric acid. I have 0.05. So I have an excess of hydrochloric acid. And since I have an excess of hydrochloric acid, it means that magnesium is my limiting reagent. And having known, when we now know that, we can now calculate the volume of gas produced. Okay, so what we now need to do is say that magnesium produces, and the gas was hydrogen gas. So if we go back, we can look at the equation, and here it is, magnesium produces hydrogen gas, and that ratio is 1 to 1. Excellent for us. That it's such a simple ratio. So that ratio is 1 to 1. Okay, which means that 1 mole of magnesium produces 1 mole of hydrogen gas. We actually have 0.02 moles, so that's going to produce 0.02 moles of magnesium of hydrogen gas. Okay, and so now we have 0.02 moles of hydrogen gas, and we're now being asked what volume that occupies at STP. So we know that 1 mole occupies, what does that say? 22,400 centimeters cube at STP. We have 0.02 moles. So how much would that occupy? We don't know, so we call it X. Okay, and then we can cross multiply. So X is going to be equal to 448 centimeters cube. Okay, 448 centimeters cube. Please do not write dm cube, because if you do, you're going to lose the mark for that question. Okay, so we can proceed now to the next bit. All right, it says calculate the energy change for the reaction between magnesium and hydrochloric acid. Assume the specific heat capacity of the solution is 4.2 joules per gram per Celsius, I suppose, and the density of the solution is 1 gram per mil, 1 gram per centimeter cube. So you're using the equation heat change is equal to mc delta T. So all you need to do for this now is say the mass of the solution, or the mass of the water, the hydrochloric acid, was 100. Okay, so that's what we're going to use. 100 centimeters cube times 4.2 times the change in temperature, which we got at 20 degrees Celsius. Okay, and so when we do that calculation, what we get from that is, so what we get here is 8,400. Okay, and of course this is going to be in joules, because this is degrees Celsius and this is 4.2 joules per gram per degree Celsius Kelvin. And so that cancels that. But notice here I have 100 centimeters cube. But notice they say 1 gram is equal to 1 centimeter cube, because that's the density. So I can convert this from centimeters cube to gram. And so my grams can cancel there and leave in joules. So 8,400 joules, right? Of course, your numbers may differ a little bit because you had to interpolate the change in temperature from the graph. So there may be some very small nuances, but it should work out to be something very similar to that. Okay, hence determine the energy change per mole of magnesium. So what happens was that when we added 0.48 grams of magnesium, we got this energy change, right? 0.48 grams, which is equivalent to 0.02 moles. So basically, when we added 0.02 moles of magnesium, right, that gave us a heat change of 8,400 joules. Now, what if we had 1 mole of magnesium? How much would we get from that? And that's what this question is asking us. So now since we don't know, we just call that X. And X is going to be equal to, let us just work that out right now. That is 420,000 joules. But your examiner loves for you to write your answer in kilojoules. So you just move your decimal point 3 places back, and that's 420 kilojoules per mole. Now, the question is this reaction endothermic or exothermic? We worked that out already. It is exothermic. And to show that the reaction is exothermic, we simply put a minus there. We're not saying that we have negative energy. We're just saying that this reaction is exothermic. That's all, by that sign. All right? So let us proceed now. All right, so this next question, this is question 2. Steels are alloys widely used in industry in place of iron metal. All right, so steels are alloys widely used in industry in place of iron metal. Define the term alloy. An alloy really is a mixture of metals with other things. So you have metals combined with other things, right? And so therefore, that's really what an alloy is. All right, so now it says name 2 types of steel, and we have like stainless steel, and we have Damascus steel, we have Hatfield steel, and a number of other steel, which, you just need to memorize those sort of things to go into your exam. Okay, so we press on. It says many metal nitrates undergo thermal decomposition. The relative ease of decomposition and products formed can help determine their place in the reactivity series. Table 2 below shows the products formed from let me zoom in a little bit. The products formed from heating of nitrates of 5 different metals, V, W, X, Y, Z. Okay, products formed from thermal decomposition of nitrates, right? And then now it says metal nitrate V, X, and Y. Their products form metal oxide, nitrogen dioxide, and oxygen gas. And metal for W and Z, you have metal nitrite and oxygen gas. Okay, so now it says using the information in the table, state which metals would be the most reactive metals and which metals would be the least reactive metals. Well, from our metals and non-metals unit, we remember that the lesser reactive metals, actually, they would decompose to form these things. So something like lead nitrate, for example. Lead nitrate. If lead nitrate were to decompose, it would form lead oxide, nitrogen dioxide, which is the brown gas, and oxygen gas. Okay? So that's what would form. And so therefore these oxides are the lesser reactive ones. And these ones are the more reactive metals of the more reactive nitrates. Okay. So you'd have to take that from that section of your syllabus. Okay, if one or more of the reactive metals was identified as sodium, write a balanced chemical equation for the decomposition of sodium nitrite. So again, 2 marks for that. It needs to be balanced. So sodium nitrate, NaNO3, and of course this is aqueous, right? And this decomposes, and if we go back, it says go to the table and get it, sodium nitrite plus oxygen gas. So we're going to get here sodium nitrite, NaNO2 plus oxygen gas. Okay, and then now of course you need to balance this equation. So now to balance that, because you must balance that, you put a 2 there and you put a 2 there, right? So you have 2 sodiums, 2 nitrogens, 6 oxygens, and you have 2 times 2, 4, plus 2 over there. So that is 6 oxygens as well. Then now the question says further tests were carried out, right? Further tests were carried out with metals V, X, and Y. Each metal was the oxides of the other metals in displacement reactions. So let me read that again because that was not clear for me. Further tests were carried out with metals V, X, and Y. Each metal was the oxides of the other metals in displacement reactions. V did not react with any of the metal oxides. X reacted with the oxides of V and Y, successfully displacing the metals. Y reacted with oxide of V, successfully displacing the metal. So what they're going to really ask you to do here, which is kind of, you can see kind of down there, is to give the order of reactivity. And the thing about it is that a more reactive metal will displace a lesser reactive metal from solution or from a mixture. So the fact that V did not react with any of the metals tells us that V is the least reactive of all the metals. Okay, so it's lowest on that reactivity C. So we're going to put it at the bottom. Then it says that X reacted with the oxides of V and Y successfully. So X must be the most reactive. And of course, there's only one left, which is Y. So that's right there in the middle. So your order of reactivity, depending on what they ask you, is X is the most reactive, V is the least reactive of those metals. And let's see if that's what they ask us. Wait. There you go. Use the information to deduce the order of reactivity of metals V, X, and Y from most reactive to least reactive. So what did we say? It was X, Y, V. So X, Y, V. All right, we press on. Okay, so let's press on to the next question, right? It says tests were carried out on a solution A to determine the cations present. The observations are presented in table 3. Complete the table by inserting the inferences based on the observations. So a few drops of dilute sodium hydroxide were added to a small portion of solution A in a test tube. It says a green precipitate was formed, which is indicative of a certain cation. right? And so I did a video about qualitative analysis. You can find the video in the link, a description, the link for the video in the description, right? So you can look at that to find out all of these things. And there's a nice little document talking about all these things, right? But once you see a green precipitate, you know that the metal you're looking at is iron 2 plus. Now, something interesting here. The green precipitate darkened when left to stand and turned orange at the top. Now, the only thing I can surmise from this is that the iron 2 was oxidized to iron 3, right? And iron 3 actually has a little, what would you say? It's a brownish color. And it may be seen as orange in this case. So the iron 2 is being oxidized there, I would suppose, to give you that. It says now a few drops of dilute sodium hydroxide were added to a small portion of solution A in a test tube. So we added sodium hydroxide. Now the test tube was heated gently. Colorless gas evolved with a pungent odor. Gas turned damper and litmus paper blue. And of course, once you see pungent, there's only one thing, one gas that we're accustomed to at the Csec level, which is pungent, and that is ammonia, right? And of course, ammonia is a basic gas, so it's going to change dampered litmus paper blue for that purpose. Okay, and so yeah, ammonia. Colorless solution formed, and the ammonia, because the ammonium salt which is formed is soluble, that's why you end up with a colorless solution in this situation. Of course, no precipitate would be formed in this situation. So we write no PPT formed. Okay, because with that you get no PPT. All right, just a little qualitative there. So we press on. It says figure 3 shows compounds A and B, which are from different homologous series. State the homologous series to which compound A belongs. So clearly, when we're looking at this functional group right there, so that's an acid. And this is, of course, an alkene. Alkene. And they will ask us about that shortly, I'm sure. So that's an acid. State the functional group of compound A. State the functional group. It's an acid functionality. So you could say that it's acid functionality for that one. All right. State the name of compound A. So let's see now the naming of compound A. It has 1, 2, 3, 4 carbons. So this is going to be butanoic acid. Okay, so the name of compound A is butanoic acid. State whether compound A will undergo a condensation reaction or addition polymerization reaction with alcohols. And of course, with alcohols, it's going to be a condensation reaction, right? Because water is produced as a result of that reaction. Then state the homologous series to which B belongs, and we did say that already, that B belongs to alkenes, right? It has 1, 2, 3, 4 carbons in it, because chances are they're going to ask us to give the name. Write the functional group of compound B's, which is carbon, double bond, carbon. State the name of B, so I'm just going to go back so we can see B and name it properly. So it has 1, 2, 3, 4 carbons, right? So that's butene, but we need to give the position of the double bond. And so therefore the double bond is between carbon number 1 and carbon number 2. So it is but1-ene or 1-butene. Right, but1-ene or 1-butene. I prefer 1-butene, but of course it doesn't matter which one you write. It's still the same thing. Okay, so we are gonna go ahead. It says here, figure 4 shows compound C, which has structural isomers, right? So figure 4 shows compound C, which has structural isomers. So the structure is going to change. Define the term structural isomers. So iso means the same. So they have the same unit pretty much. They have the same molecular formula, but different structural formula. So this species here could have a different structural formula they're suggesting. So that's the definition of structural isomers. Same molecular formula, but different structural formula. Okay, so same molecular, different structural. All right. So let's see. Next question now. All right. So now our next question says draw the fully displayed structure of two isomers of compound C. Now, when they say fully displayed structure, you must, and I didn't do it here, but you must, and I'm just going to show you for one part. Actually, let me show you for this part. You must draw out all the carbons connected to each other and all the hydrogens connected to each other. So you need to have it looking like this, right? So you need a hydrogen there, hydrogen there, hydrogen there. And that's going to be the same thing for this, right? Same thing for this. This is CH3, this is CH3, this is CH3. Okay, but it must look like this over here. I just want to point that out. I'm just showing you this for simplicity purposes, just for the purpose of the video. But when they say fully displayed structure, that's what you need to do. So the thing about it is that the compound had actually, here's the compound, 1, 2, 3, 4, 5 carbons and 2, 4, 6, 8, 10, 12 hydrogens. Right? So we need to make sure we draw structures with that same number 1, 2, 3, 4, 5, 3, 6, 9, 12. There you go. And here's another one over here. Right? Remember, you have to draw it your hydrogens. So that's 1, 2, 3, 4, 5, 3, 6, 7, 8, 9, 10, 11, 12. Okay? And that's how we get our isomeric forms for this species. All right? Then now it says write the names of the two structural isomers you have drawn. And let's just go back so we can give them their names. So let's look at this structure. This structure has 1, 2, 3 carbons, 1, 2, 3, 1, 2, 3, 1, 2, 3, in any direction. And I've done a video about naming branched alkanes. You can check out that video, and there it is right there now in the top right of your screen, right? You can check out that video on that. But the name of this species, it has 3 carbons in the longest chain, and it has 2 methyl groups attached right there. So this species is actually 2,2-dimethyl propane. 2,2-dimethyl propane. So that's the name. 2,2-dimethyl propane. There you go. Okay. And of course, you must remember your commas between your numbers and your hyphen between your numbers and your letters. This species over here now, 4 carbons in the longest carbon chain, 1, 2, 3, 4, and there's a methyl group on the second carbon. So this is 2-methyl butane. 2-methyl butane. There you go. And you collect those marks and you press along. All right. So those are the names of the two species, which you'd write on that line, of course. Question 4, we're doing nicely. Figure 5 shows a line diagram representing the electrolytic cell used in the electrolysis of aqueous, and this is important, aqueous copper sulfate solution using copper electrodes. So therefore, these electrodes are active electrodes. So what happens at the anode is not discharge, but actually the anode is going to dissolve, and we're going to see that shortly. Okay, so let's see what the questions are asking us now. It says state whether the electrodes used are active or inert. There you go. Give a reason for your answer. So they are active because they can dissolve in the electrolyte. And that's it. Because they can dissolve in the electrolyte. So they dissolve in the electrolyte, and that's why they're active. If they were not active, they would not dissolve in the electrolyte. Okay. All right. So we are going to press along. Okay, it says describe what occurs at the cathode and at the anode in the electrolytic cell. So I'm just going to go back to describe it. So because you are using copper electrodes, right, and it's copper sulfate, the ions in solution would be copper ions, H plus ions, sulfate ions, and OH ions. Normally, you'd expect that the OH ions would be preferentially discharged at the anode. However, in this situation, what happens that because you're using active electrodes, which is the copper metal is going to dissolve in the electrolyte. Then now you have 2 cations which are competing for discharge. And because copper is lower than hydrogen in the electrochemical series, copper will discharge. So what you expect to happen here is you're expecting that the anode is going to get thinner, the cathode is going to get bigger, and the electrolyte is going to become paler as the reaction proceeds. Okay, so those are the things that you're expecting to happen. So let's see, right? And well, it's just 2 marks. Wait. Okay, so describe what occurs at the anode and the cathode in the electrolytic cell, and that is what happens. Describe what occurs at the cathode and the anode in the, okay, so that's just 2 marks. So basically, the anode dissolves and the cathode becomes fatter, or it's coated with copper. Okay, state at which electrode in figure 5 on page 16 is the cathode and which one is the anode. So just remember now, cations go to the cathode and anions go to the anode. Cations to the cathode and anions to the anode. Okay, now this section of the power source is connected to here, the positive section. If anions are negative, they're going to go to the positive side. So this side is your anode. Okay, and this side is negative, cations go to the cathode, so therefore cations would go over here. So this is our cathode, because they will only go to the oppositely charged section. So A is the anode and B is the cathode. So you write A and B, right? Then now identify the ions that will migrate to the cathode. We kind of just said that already. So the cathode would have copper ions going there and H plus ions, and to the anode you have sulfate ions. They go there, and OH ions. Even though they don't become discharged, they still go over there. All right. So then now it says write half equations to show the substances produced at the cathode and at the anode. And as I said earlier, at the cathode, you're expecting copper 2 plus ions aqueous to be discharged. So this is your half equation that occurs there. Copper ions are converted to copper solid. And at the anode, where the copper discharges, it's actually the reverse of the above reaction. Copper dissolves to form copper 2 plus ions, which is aqueous, plus 2 electrons. Okay, so that is what would be the equations. Using your answer in part B to explain why a redox reaction took place during the electrolysis of copper 2 sulfate. Well, of course, redox reaction involves the transfer of electrons. Um, of electrons, right? That's generally the case. But for the purposes here, you could also say that the oxidation state of the copper in solution was changed to 0, and the oxidation state of the copper in the metal was changed to 2 plus. So that's another reason why you could say that it is a redox reaction. The oxidation state changed and there's a transfer of electrons. You probably want to put both of them, all right, since it's about 2 marks for that question. Okay. Then now suggest one change that is likely to be observed at the cathode. And we have said this already, that the color may change. So at the cathode, you're going to get copper. Copper is kind of reddish brown. So you're going to see the copper looking red right there. You'd see a deposition, or you may see it getting a little bit thicker if you were very keen in your observations. All right. So we go ahead. Explain how the electrolytic cell can be modified to plate copper onto a small piece of steel. Now, for this purpose, all you need to do is take the steel and put it at the cathode. So replace the copper in the electrolytic cell with the steel, and it will be coated with the copper. And that's pretty much it. All right, so next question, it says state 4 general characteristics of the homologous series, right? One, there's a general formula for each class in the homologous series. They have the same physical properties. Generally speaking, consecutive members differ by CH2 or a mass of 14, because carbon is 6, 12 actually, and hydrogen is 2, so 12 plus 2 is 14, right? um there's a graduation in properties along the series, meaning that as you move along from methane, ethane, propane, butane, pentane, hexane, etc., you get a change in physical properties, a gradual change in physical properties. So you may move from gas to liquid to solid. You're going to have an increase in melting point. You're going to have an increase in boiling point. Okay, so they have the same general properties. There's a difference between consecutive members of CH2 or a mass of 14, or you could use both of those as two different things. there's a functional group which governs each of the classes of compounds, right? And that's 4 marks, so you need to give 4 things. Let's see now. All right, well, hold on, let's go back. Right, so yes, it says now write the general formula of an alcohol, of the alcohol homologus series, and the molecular formula of the fifth member. So alcohols, their general formula CnH2n plus 1OH. Now the fifth member of the series means that there are 5 carbons, so we're going to replace N with 5. So that's going to be C5, and I should just, yeah, C5. H 2 times 5 is 10 OH. N plus 1, sorry, 11. So 2N plus 1, 11 OH. So there you go. C5H11 OH. All right. Figure 6 shows the fully displayed structure of compound D. Circle any 2 functional groups shown. So here's a functional group, that's acid. Here's another one, that's alkene. Here's another one, that's ester. So this is ester. This is alkene. And this is acid. Okay, there's no E on acid. All right, so we proceed. It says experiments were carried out on 2 hydrocarbon gases and gas samples E and F to determine which gas is ethane and which is ethene. Hydrocarbon meaning there's no oxygen or anything, it's just hydrogen and carbon. Table 2 represents the experiment and the observation. So experiment, each hydrocarbon was bubbled through bromine. Hydrocarbon E, orange bromine water becomes colorless, no reaction. It should be clear now. State the difference between alkanes and alkenes. State the difference. Well, one, alkenes are more reactive. They undergo addition reactions. And alkanes are less reactive and they undergo substitution reactions. Okay, so that's one difference there, depending on the number of marks. Yes. So use the observations in table 4, identify hydrocarbons E and F. They did not mention any light, so no light was mentioned in this. So if there's no light, then the reaction of bromine with the alkene, so E is the alkene, would occur in darkness. They didn't mention any light or anything like that. If E did not react, well, F, sorry, if F did not react, it means that this is the alkane, because for an alkane to react with a halogen, you need some light. Okay, so where I'm going to assume that there was darkness here, and this is, of course, the alkane. All right, so that's that. State the conditions under which an alkane would react with bromine, and I kind of just said that in light. So you need light for that. You need some irradiative source. All right, so then now it says write. Let me see if I have this question on the other page. No, I don't. It says write a balanced chemical equation including state symbols for the burning of ethene gas in air. Okay, so we just want to write an equation for ethene gas. So that is, ethene is C2H4, and then that's plus oxygen, and I'm just going to erase this so I have some space here, right? Okay, so I just erased that. And of course, this is going to give us carbon dioxide and water. So CO2 plus H2O. And this is what we're doing here. Write a balanced chemical equation, including state symbols. So ethene is a gas, oxygen is a gas, carbon dioxide is a gas. And under these conditions, the water is going to be a gas as well, because you're burning it. So you're going to get a gas. And let us balance this equation. There are 2 carbons over here. So we're just going to put a 2 right there. We have 4 hydrogens here, so we're going to put a 2 right there. Now we have 4 oxygens here plus 2, so that's 6. So we'll just put a 3 right there. And that's our balanced equation. We proceed. Okay, question 6, which is actually, I think, the last question. A chemical factory produces pesticides, fertilizers, and plastics using synthetic raw materials. The factory has been in operation for the past 5 years and is located near agricultural lands in a small rural community. Recently, the residents of the community have reported significant loss in plant and animal life due to increases in air pollutants, non-biodegradable solid waste, and algal blue growth in nearby waterways. The increased toxicity has impacted the local agricultural economy. State two examples of air pollutants. So something like SO2 and NO2, those are air pollutants. Of course, dust, air pollutant, smoke, air pollutant. All those things are air pollutants, right? Let me see if we have this one over here. Okay, so now it says suggest three substances found in the products produced by the chemical factory that may have contributed to the increased algal growth in waterways. So this is coming from biology to some extent. To some extent, where you have algal blooms, and of course, algal blooms are caused from increased fertilizers. So things like nitrates, that's going to improve phosphates, is going to cause that, and ammonium based species, so ammonium salts, those sort of things are substances which will cause increased algal growth in waterways. And of course, if they have any potassium based substances as well, then those things as well. Finally, it says define the term green chemistry. You could define this in so many ways depending on how you're looking at it. um, so green chemistry really looks at sustainable development in chemistry. And the word sustainable really means that you are not using more than you have to, so that future generations will have an earth to live in that is not polluted or contaminated. So basically, if you're going to define green chemistry, you're saying that green chemistry is a part of chemistry that looks at the sustainable use of chemistry, or the sustainable practice of chemistry, so that future generations will not be suffering from the consequences of our actions in today's world. All right, so here we go. This is the last list three principles of green chemistry. So in terms of principles of green chemistry, you're looking at things like atom economy, you're looking at atom economy, less hazardous chemical synthesis, designing safer chemicals, safer solvents and auxiliaries, and the list goes on. Green chemistry is something that they do mention that is going to be on your exam, so you want to make sure you know those things so that you can get these marks. Design for degradation, that's another thing which is on there, so you can have a look at that. Okay. And this is our last page. Explain how any three principles of green chemistry can be used by the factory to minimize the impact of pollution on the local agricultural economy. Look at the question now. You notice that they are using synthetic raw materials. What they could use is design materials for degradation, so make things more biodegradable, and that will also help. They could also use, because one of the principles is real-time analysis of pollution. So because these things are having an impact, they could look at the immediate impact of these substances on the environment. And finally, use renewable feedstocks. So basically, what you want to say here is that whatever they're using, it can be cycled through the system again. Okay. All right. All the best.